Hey everyone, welcome back to my number sense series. In this video, we're going to talk about geometric sequences. So previously, we've talked about arithmetic sequences, in which each term is the previous term plus something. So what is a geometric sequence? Well, let's take a look at probably the most famous example of a geometric sequence. 1, 2, 4, 8, 16, blah, blah, it goes 32, 64, 128, on to infinity. So some of you have probably figured out the pattern already. In this sequence, each term is the previous term times 2. And so you might kind of be able to guess what a geometric sequence is. It is a sequence in which each term is the previous term times a number, as opposed to adding in an arithmetic sequence. And so we have a new variable to denote this called r, where r is the common ratio, as opposed to the common difference that we would have in an arithmetic sequence. So a geometric sequence is honestly not too much harder than an arithmetic sequence. So, as we did with an arithmetic sequence, let's try to determine a formula for a geometric sequence. So we have a1 equals 1, a sub 2 equals 2, a sub 3 equals 4, a sub 4 equals 8, a sub 5 equals 16. So we would like to determine a formula for the nth term. Well, we know that what we get in a geometric sequence is essentially repeated multiplication, and we have a name for that. It's called exponentiation. And so we might want to express each of these as exponents. And of course, we have a very natural base for the exponent, which is 2. So 16 is 2 to the power of 4, 8 is 2 to the power of 3, 4 is 2 squared, 2 to the 1th, and then 2 to the power of 0. In case you didn't know that, any number to the power of 0 is 1. So we have all of these. I noticed that the power that we raise 2 to is always 1 less than the index of the sequence. So for example, the 5th term is 2 to the power of 4, and so we can kind of infer that like the 6th term would be 2 to the power of 5, the 10th term would be 2 to the power of 9, the 100th term would be 2 to the power of 99. Always 2 to the power of n minus 1, where we are trying to find the nth term. So we can suppose that this is the formula. But of course, a should also matter in a geometric sequence, right? If we start with a different number, we're of course going to end with a different number because every number depends on the previous one. And here, a does kind of influence the geometric sequence, just not in this case, because we are multiplying by a, and when you multiply anything by 1, it stays the same. But just know that there's an a in here also. So our general formula for any arithmetic sequence, given a starting number a and a common ratio r, is going to be a sub n equals a times, what's 2? 2 is r to the power of n minus 1. And you can see it's actually not too different from what we had within arithmetic sequence, because in an arithmetic sequence we had a plus d times n minus 1. And so the only difference really is that we have r instead of d, and now instead of repeated addition, we have repeated multiplication. So instead of multiplication, we have exponentiation, if that makes sense. So that is the general formula for the nth term of a geometric sequence. So let's move on to applying this formula. What is the next term in the sequence? 2, 6, 18, 54. So like the arithmetic sequence video, this one we don't really have to apply the formula, but it's just a test that you know what you're doing. So in order to find the next term, we have to know the previous term, which we have right here, and we also have to know r. So what is r? Well, just like with an arithmetic sequence where we could get r by finding the difference between two terms, here we can find the quotient. So r would be 6 over 2, or 18 over 6, or 54 over 18. They're all the same, which is 3. So we infer that the next term is 54 times our common difference, which is 162. Not too bad. Now, our next question requires us to apply the formula a little bit, maybe, to skip some steps in our head. So what is the sixth term in the sequence? 3, negative 6, 12. Okay, first of all, there's something interesting about this one. We have a negative term. We have positive, negative, positive. What does that mean? Well, this just means that r is negative. When we multiply a positive number by a negative number, we get a negative, and then when we multiply that negative by a negative, we get a positive. So you can see that r is actually negative, and that causes the sign to oscillate. But that's not really a problem for our formula, right? Like nothing really breaks. So let's just apply the formula. The sixth term is going to be a times r is going to be -2, because it's -6 over 3 or 12 over -6, either of those. 3 times -2 to the power of what? N minus 1, which is 5. And that's going to be -96. Hopefully you are familiar with your exponents. If you're not, that's okay, but I would definitely try to memorize at least the powers too, because they're going to be pretty important. All right, so that's that. Then we ask ourselves, what is the 8th term in the sequence? 1 over 8, 1 over 4, 1/2. So this one is also a little bit different from the others because now we have fractions. And fractions, like negative numbers, are totally acceptable in a geometric sequence. So we can simply pretty much apply our formula again. What is the 8th term in the sequence? 1 over 8, 1 over 4, 1 over 2, blah, 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 blah. Well, our formula is a times r to the power of n minus 1. So we have 1 over 8 times, what's r here? Well, r is 1/4 over 1/8, which is 8 over 4, which is 2. And we would get the same answer if we did 1/2 over 1/4. So, 2 to the power of what? The power of n minus 1, which is 8 minus 1, which is 7. So we get 1 over 8 times 2 to the power of 7. Again, this would be a nice time to know your powers of 2, which I would recommend memorizing up to 2 to the power of 10 equals 1024. This is 1 over 8 times 128 equals 16. So you can see it's not too different from an arithmetic sequence, only here we just have to do exponentiation instead of multiplication, really. Now, with geometric sequences, just like with arithmetic sequences, we can add them, but it is much harder to do so with geometric sequences. It does get a little bit easier if the geometric sequence is infinite, but I'm going to say it's still not easy at all. And the only questions that will ask you for the sum of a geometric sequence are going to be questions in like the 70s, like the very, very back part of a test on maybe like a state or a national level. They're going to ask you about the sum of an infinite geometric sequence. So if you're just trying to get to, question 40, 50, 60, I would not worry about this. But if you intend to go to this level, or if you are simply curious, which I hope you are, stick around for this part. But if you're not, this is really all you need to know. But if you want to know how to sum a geometric sequence, an infinite one, because that is all they'll test you on, watch the video. So, the sum of an infinite geometric sequence, 4, 3, 9 over 4, blah, blah, blah. Now, I would like to derive this actually, because if you're here, it is absolutely very good for you to know where the formula comes from. And also, if you're curious, this is hopefully going to satisfy your curiosity. So let's start without using variables, just so we don't get anything confused. And then after that, we can translate the proof to variables. So we have, what's the sum of the series? So let's just write the series out. 4 plus 3 plus 9 over 4. We know that the common ratio is going to be just 3 over 4. So we know that the next term would be something like 27 over 16, then 81 over 64, blah, 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 blah. Okay. We'll call this number S. S for sum. And so our goal is to find S. Now here is a very inspired idea, a very important idea, and the idea that's going to carry us throughout this proof. We're going to multiply S by R. Okay? So we have 3 over 4 times S. So we're multiplying both sides by 3 over 4. And what do we get on this side? We get, well, 3 plus 9 over 4 plus 27 over 16. So this is what you get when you multiply each of these terms by 3 over 4. Plus 81 over 64. And wait a second. This looks kind of familiar, right? This term equals this term, this term equals this term, this term equals this term. And of course this should make sense, because when you get from 3 to 4, from 4 to 3, you're multiplying 4 by 3/4. And also to get to here, you're multiplying it by 3/4. So the smart idea is to subtract these. If I subtract these two equations, what I get is S minus 3 over 4S equals 4 4 what? Well, this cancels out, this cancels, this cancels, this cancels, everything cancels except the 4. So we have s minus 3/4 s equals 4. And so we have 1/4 times s equals 4, and so s equals 16. That's such a nice number, right? And of course, it's not a coincidence. If we were to translate this proof here, what we would find is that we are essentially stating s equals a plus ar squared plus ar cubed, blah, blah, blah. And then we are multiplying both sides. So we have s times r equals ar plus ar squared plus ar cubed, blah, 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 blah. And then when we subtract both sides, what we get is s times 1 minus r equals a, because ar squared, again, all of this cancels out. And so we can just divide both sides by 1 minus r to get s equals a over 1 minus r, which is like beautiful. This is our formula for the sum of an infinite geometric sequence, a over 1 minus r. And we can confirm this by plugging it in. So we have 4 over 1 minus 3/4, which is 4 over 1/4, which is indeed 16. Also, one last disclaimer. This only works if the geometric sequence decreases, okay? Obviously, if r is greater than 1, if r is 2, for example, the geometric sequence is going to blow up and it's never going to sum to a number, okay? It's just going to go to infinity. So only apply this when r is between -1 and 1, because only when r is between -1 and 1 will the geometric series, well, this is now a series, will the geometric series do what we call converge. Basically, well, converge, not go to infinity, essentially. Only do it with this, but I'm pretty sure number sense will just only have these cases for you. So as long as you memorize a over 1 minus r, you should be good for this. But in case any of you were curious about the proof, I think it's very beautiful and worthy of thinking about. So hopefully that satisfies your curiosity. That is it for geometric sequences. These, not too much difference from arithmetic sequences. Just know that it's exponentiation instead of multiplication, and we, change one of the names of the variables. Not too much harder. If you intend on doing the sum, awesome, and it's not too hard either to memorize the formula. It's actually very simple. And yeah, the geometric sequences, arithmetic sequences. Next time we're going to do other kinds of sequences, but I would say these two are the foundational kind of sequences, and if you understand everything on this board right now, you're going to be very well set. Thank you guys for watching, and I'll see you next time.